Hey everyone, in this video we'll be finishing up our cycling state by adding in two types of additive leans. One where the character leans in the direction that it's turning in, and another where the character leans into the direction of its acceleration. I'll be using animations from the unarmed upright strafing animation set, but the two sets of leaning animations, the Lyra style animations for turning, and the advanced locomotion system style animations for the additive acceleration-based leans can be found in the respective projects, and you will be able to follow along fully using the Lyra leaning animations and the advanced locomotion system version for leaning animations. With that said, let's get started. The animation set that I'm using, the unarmed upright strafing animation set, has lean animations in two styles, a Lyra style and an advanced locomotion system version for style. The Lyra style leans get applied to a character to lean the character into the direction that a character is turning in, while the advanced locomotion system style leaning animations are meant to lean the character into their acceleration. So as they speed up, the character leans forward. As they slow down, the character leans backward. If you're not following along with the UUS animation set, you will be able to follow along with the Lyra animations. Let's go ahead and take a look at one of these lean animations because there's something special about them, different from other animations that we've worked with so far. These animations are additive animations, meaning that they're being considered relative to a type of base pose for the character. When we apply them in an animation graph, it applies the difference between the additive animation pose and the base pose selected in the details panel of the additive animation to a pose that we input in our graph, which allows us to input a variety of poses and have them offsetted in a way that makes sense. An animation can be set to be an additive one by going into its details panel and changing the additive animation type from no additive to a local space or mesh space. Now I'm going to go ahead and open up this jog lean animation to explain the difference between local space and mesh space. Local space is when a bone's rotation is considered relative to its parent. So here we have this forearm bone. It's about 90 degrees away from this upper arm bone. So when considered in local space, its rotation is going to be roughly 90 degrees along one of its axes. However, in mesh space, its rotation is considered relative to the rotation of the root bone, and so it's going to be different as it's being compared to the root bone and not the bone directly above it in the skeletal hierarchy. There are some different ways we can choose a base pose for an additive animation. We can choose a skeleton reference pose, which would be the A pose. And for some reason, I found that my sequence viewer has not been updating, so we're not able to actually see the difference. We can choose an animation scaled to fit the length of the additive, an animation frame, or a frame from this additive animation. We're going to leave this on selected animation frame. And I'm going to go ahead and undo, and we can see that the animation selected here by default for this asset is itself. And because this is a center lean, being additive to itself means that it's not going to offset the actual pose of the character. If we look at the left lean, it is relative to the center lean, and the same is true for the right lean. So the jog left lean is relative to the jog center lean animation, and the jog left lean and right lean are also relative to the walk center lean animation. This means that we'll get a very predictable additive offset when we apply these animations in the graph. So now that we understand how we can set up an additive animation and how they should be set up for the system that I'm going to implement, I'm going to close out of the sequence, open the content drawer, and go ahead and create a Blendspace asset. I'll name it to bs_n_lean_turn. If I open it up, you'll see that we have a graph here that has two axes, a vertical and a horizontal. Now, what the Blendspace does is it blends between the animations that we place into this graph at runtime based on the value we provide for each axis. There are 1D Blendspaces and 2D Blendspaces in Unreal Engine, and I'll be showing you more ways we can use Blendspaces in the future of this series, but in this video, we'll stick to using them for applying additive leans to our locomotion. I'm going to go ahead and give each axis a name and a proper value range. I'll name the horizontal axis LeanAngle and the vertical axis Gate. I'll set the minimum value for the horizontal axis to -90 and the maximum to 90. I'll leave the minimum value for the gate axis at 0, and I'll set the maximum value to 2. 2 will correspond with jogging, and 1 will correspond with walking. We can also set the amount of grid divisions in the grid of this blend graph. I'll go ahead and set the divisions to 2 for each of these. Now, one more option, for now at least. I'm going to enable snap to grid for both of these, which will snap the animations that we drag in to the grid. From the top layer, going left to right, I'm going to place the jog lean additive animations. The left one will go on the left, the center one will go in the center, and the right one will go on the right. Now our character has disappeared, and that is because we need to set a preview base pose. Now this got set automatically to the jog lean center animation, which is already an additive, and now this preview base pose does not override the base poses of these animations, but rather it's a preview of the base pose you'd input into an animation graph. So I'll select the jog loop forward animation, and now, as you can see, well, it looks like this isn't correct. I accidentally placed the incorrect animation into the center, so I'll delete that out and bring in the center animation. Again, it tried to change that preview pose, so I'll change that back to the jog. Now, if I hold Control and move my mouse, we can see the additive being applied to the jog animation as I move my mouse back and forth. And in the same way we are seeing it applied to this jog animation, that is how it will apply to the input pose in our animation graph when we set this up. Next, I'll bring in the walking animations for leaning. The walk lean center will go in the center, left will go to the left, and right will go to the right. And I'll go ahead and change this one more time. I'm not sure why it keeps changing back to that jog lean animation. Now we can see the lean being applied. There's a bit more of a lean for the jogging than there is a walking, and that's the main difference between the additives here. I'll go ahead and save this, and I'll come back and revisit these settings later on. I'll go into the Locomotion layers animation blueprint and go into our cycle state. And between our sequence player and our orientation warping and stride warping, I'm going to right-click and search Additive. There are 2 nodes here that will apply additive animations to a character, an apply additive node and an apply mesh space additive node. We want to use an apply additive node, as this node will work properly with local space additives, and the mesh space one will work properly with mesh space additives. For the additive pose, I'll go ahead and bring in our Blendspace for leaning and turning that we've just created. And I noticed I did not capitalize the L for the LeanAngle variable name, or input name I mean. I'll go ahead and fix that now. I'll save, and back in Locomotion layers, we need to supply some inputs. we already had the gate enumerator in our main animation blueprint. I'll go ahead and get a property access node, and I'll go ahead and get our main animation blueprint and get our current gate. Now this is an enumeration, while this input expects a float. I can drag out from it and search select and choose a select node, and now based on the value of this enumeration variable, we can select a value of any type, depending on what we plug this return value into. So I'll plug this into gate, and it's automatically set to these two values for walking and jogging to floats. So walking, I'll set to 1, and jogging, I'll set to 2. And now the proper animations will be used when we are walking or jogging. Now, this will be an instant transition, and that is not going to be ideal, but Blendspace assets have some settings we can use to interpolate automatically between different animations, and it's very useful. It's controlled by the smoothing time variable, which is independent for each axis. I'll set the smoothing time, in this case, to a value of 0.5. And that will be true for both axes. Now, you can see it takes a bit of time for this green X to actually make it over to my cursor, which means that this smoothing is being applied. I'm going to leave the type as spring damper for both, as well as the other two settings here specific to the smoothing type. I'll save this again, and I'll go ahead and cover one more setting here. The input interpolation type. I'm going to go ahead and toggle on use grid, and you'll see those lines drawn between the different animation sequences disappear. What those lines represent, if I turn this back off, are which animations are being blended between. It'll try to choose a set number of animations to blend between on the graph, and it will either use a tangential triangulation direction to figure this out, or a radial. And we can see that the lines drawn between these change. Now, in most cases, one or the other will work, but the grid version is calculated at runtime, costs a tiny amount of performance, but will result, in my opinion, in a better blend. So I'll leave this on grid. You can experiment with these settings and go with what works best for you. I'll go ahead and save this. And now we don't need to do anything else within this lean turn Blendspace. All of our settings are set. And now we just need to figure out how to calculate a lean angle float. I'll calculate this in the base animation blueprint. I'll go ahead and save and move back into the base animation blueprint and go into our blueprint thread safe update animation function. I'll go ahead and enter into our get rotation data function. I'll drag out from the world rotation node, and I'll search brake rotator and select the brake rotator option. We've now broken the rotator into its three components: roll, pitch, and yaw. We're interested in the yaw, which is the rotation around the up and down axis. I'll go ahead and drag out from our yaw, and I'll promote this to a variable named actor yaw. I'll move this into the rotation data section of our variables panel. Before we set actor yaw, I'm going to go ahead and duplicate this actor yaw variable and rename the duplicated variable to previous actor yaw. I'm going to drag this into the graph and plug it in before we set actor yaw, but after we set world rotation. I'll put previous actor yaw into the correct category, and drag out actor yaw, and set previous actor yaw before we set actor yaw with actor yaw. And what this does is it effectively saves the actor yaw from the previous frame before we set the actor yaw for the current frame. And when we have two variables, two values set over time, we can determine how quickly the yaw is changing, which is what we want to use to drive the leaning of our character. I'll go ahead and subtract the previous actor yaw from the actor yaw. This will give us the difference in yaw per each frame. I'll drag out from the result of our subtraction, promote it to a variable named actor yaw delta. I'll plug this node in so that the variable gets set. However, this is the change over frame, and that's going to be a very small value. I'm going to convert this frame by frame change into degrees per second. To do that, I'm going to get a safe divide node, and I'm going to divide it by the time between rendered frames, known as the delta time variable, or the world delta seconds. The Blueprint ThreadSafe update animation function has access to delta time. So now I'll go ahead and add an input into the getRotation data function named delta time of the type float. And I'll plug our delta time input within our Blueprint ThreadSafe update animation function into the delta time input for a getRotation data function. And now I can right click within our function and search delta time and access the input variable. Dividing a value that's on a per frame basis by the delta time, or the time between frames, will convert it to be on a scale of seconds rather than a scale of frames. The result of this value is what I'll use to set a LeanAngle float. But before we do that, I'm going to go ahead and get another divide node here. This can just be a normal divide, as we're not going to be dividing by 0 at any point, and we shouldn't be by delta time, but we're just being safe because don't have direct control over the value that we're placing in here. I'll go ahead and divide this value by 4. You may eventually want to experiment with setting this value differently, as that's going to affect how far your character leans based on your speed of rotation. Next, I'm going to go ahead and clamp this angle between a minimum value of -90 and a positive value of 90. That way, we're never outside the range of our blend space. Finally, I'll create a new variable and set it with this result. I'll name the variable LeanAngle. I'll compile to save. Back in Locomotion layers, I will get a property access node. I'll get our main animation blueprint and get our LeanAngle node. I'll set this blend space with it. Back in the third person map, I'll go ahead and play. Now, when I move forward and turn, the additive lean gets applied while we're in our cycle state. Now, this is getting applied correctly if our hips are facing forward into motion. However, it's not getting applied correctly if our hips are facing away from motion. It's getting applied, in the reverse direction as it should be being applied in. Back in the base animation blueprint, before we clamp this angle, we're going to multiply it. And for the value we're multiplying it with, I'm going to drag out and get a select node. For the index of the select node, I'm going to get the hip facing direction, which I covered in a previous video. Now, if you did not follow along with the spin video, you do not need to use the hip facing enumerator that I created. Instead, you can get the locomotion direction enumeration from the video where we cover orientation warping and animation switching. Get a select node and set values depending on your animations specifically. If the hip facing direction is aligned with the direction of movement, you set the value to 1. If it isn't, you set the value to -1. I'll use the hip facing direction approach, as that's simpler and only 2 values need to be set. And because the hip facing direction in my case changes for the right and left directions. If I compile and play, when moving backwards, we now lean properly. And the same goes for our leaning direction when moving any direction when our hips are facing away from or into movement. All right, with that done, we can now set up our leans where the character leans into its acceleration. I'll go ahead and, at least in this project with the UUS animations, navigate into the folder that has the Advanced Locomotion System style animations. I'll create a Blendspace, and I'll name it BS_N_lean_ACCEL for acceleration. I'll set the value range for each axis to a minimum of -1 and a maximum of 1. This is because the amount we lean into our acceleration is going to depend on the difference between our current acceleration and our maximum acceleration. In this case, acceleration is being considered in the actual physical sense, not the sense that it's being considered as the variable that the character movement component tracks. In this case, acceleration is the difference between velocity over time, where the character movement component uses an acceleration value to set the velocity. In this case, we'll calculate a new physical acceleration variable that is calculated using the character's velocity, and I'll show you how soon. I'll name the horizontal axis L/R for left/right, and I'll name the vertical axis F/B for forward/backwards. I'll leave the grid divisions at 4. I'll set the interpolation smoothing time to 0.5 and leave it as spring damper, and I'll set use grid to true. Now I'll take the Advanced Locomotion System style animations for the lean poses. The forward pose will go up top, and I'll actually delete that back out because I forgot to select snap to grid. I'll bring it back in, and now we have our lean forward animation. I'll put lean left in the middle, so where forward and backwards is 0 on the left side. I'll do the opposite for the right side, same vertical value as the left side. And at the very bottom center of the graph, I'll put the lean pose for backwards. Now there is a lean pose middle animation as well, which I will place directly into the middle of the graph. Now, as I move this around, we can see we're leaning from side to side or forwards and backwards. So imagine you start running. You lean forward quickly into your acceleration, but as your acceleration lowers and your velocity stabilizes, or your velocity doesn't change as much over time, you're going to bring yourself to be more upright. But as you stop, that's probably going to be accompanied by a bit of a lean backwards before you bring yourself back up to standing upright and still. And that is the principle that we're going to be using here with how we designed the system to apply the leaning animations. That's all the settings for this Blendspace, so I'll go ahead and close out of it. Acceleration leaning is going to apply as we're starting, as we're stopping, as we're cycling, pretty much everywhere, as our acceleration can be changing as long as we're moving, and is going to have no effect when we're standing still. Instead of applying this additive animation Blendspace in the cycle state, I'm going to apply it directly in the animation graph of our main animation blueprint. As these additive animations are just additives, they don't need to really correspond with an locomotion animation set, so we can set the animation values directly, within our main graph, and that's why I didn't bother with setting the animations dynamically in an update function in our Locomotion layers graph. I'll go ahead and bring in our Blendspace. I'll get an apply additive node and plug this all in. Now, before we continue on and calculate this variable, if I click into one of these poses, we can see that it is relative to this jog base pose that is part of the UUS animation set. You can make this relative to the center lean pose or the idle or the first frame of an idle animation. That choice I'll leave up to you. I'll leave this as being relative to a jog base pose, which is a dedicated animation here. Or if you're not following along with the set, you could create a similar pose of your own, as these single frame poses are not too difficult to create in any sort of animation software. So now we need to actually calculate a variable for the left and right acceleration and the forward and backward that raises as we're accelerating and lowers as we are decelerating. And deceleration and acceleration are only differentiated when considered relative to velocity, as when it's opposed to velocity, the value will be negative, and when it's aligned with the direction of velocity, the value will be positive. That should make a bit more sense as we get into the actual calculation. So within Blueprint Thread Safe Update Animation, we're going to place this calculation within our Get Acceleration Data function. We're going to need some of our rotation variables though, so I'm going to reorder this so that we calculate our rotation data before we calculate our acceleration data. That way we're not relying on a variable that is old from the previous frame and inducing lag, however small, into our system. I'm also going to go ahead and create a delta time input for our acceleration data function. Now we need to calculate our actual physical acceleration. I'll go ahead and get our velocity variable, and we only have our current velocity for the frame. So I'll go ahead and go back into our velocity data function, and before we set character velocity 2D, we'll set a new variable named previous character velocity 2D with the value of character velocity 2D. This is the exact same pattern as we used when getting our yaw and delta. Back in our acceleration function, I'll get that previous velocity variable, and I'll subtract it from our current velocity. That'll give us the difference over frame. And now I'll go ahead and divide it by the delta time input. We can't use a safe divide on a vector without splitting it out and dividing each of its component float parts. And, well, I think that's all right, because delta time, if it were to have a value of 0, you'd have an infinite frame rate. And if the engine thinks you have an infinite frame rate, well, something has already gone very wrong. So moving on, I'll use this result to set a new variable named physical acceleration 2D. I'll go ahead and compile this. And within our event graph, I want to print out the length of this vector to show you what the values look like, as I think that'll help you better understand what we're going to be doing with this vector shortly. So I'll get the length of the vector, and I'll get a print string node. I'll input the length into the end string input, plug in the print string node to the update animation node, and I'll set the duration to 0. I'll compile, save, and I'm actually this doesn't matter. I was going to maybe disconnect this, but it's at the middle, so it's not going to have a strange effect. Now we see our acceleration is 0. If I start moving forward, Well, it has a number, but then as soon as we've accelerated to our max walk speed, it gets set to 0. You can see our acceleration is changing as we're turning, as that does affect our acceleration. If I go ahead and instead of getting the length, split this struct pin and plug in the Y value, and so depending on our direction, it's positive or negative. However, that's relative to the world and not relative to the character. What we need to do is unrotate this vector by our actor rotation so that its direction becomes relative to the character and not relative to the world. We did something similar showing you the manual implementation of stride warping in a previous video. Back in the get acceleration data function, we'll be unrotating this vector later on within our calculation. But first, we're going to clamp the size of this vector so that when we're accelerating, it never exceeds the maximum acceleration of our character movement component, and that when we're decelerating, it never surpasses the value of our maximum deceleration setting in our character movement component. So that then when we divide by either our maximum acceleration or maximum deceleration, we're always within a range of 0 to 1, at least in terms of absolute value. It will actually be a range of -1 to +1 once the vector is rotated relative to the character properly. I'll go ahead and get a property access node, and I'll move it over here, and I'll go ahead and get our character movement component, and I'll get its maximum acceleration. And because the character movement component has different values for speeding up and slowing down, we need to figure out if we're speeding up or slowing down. We know that if the character movement component's acceleration vector, which is applied to the velocity to increase it, is not equal to 0, then we have movement input and we are accelerating. At least in the sense that the character movement component expects, as that acceleration does not go to 0 when our velocity is not changing. So we can use the previously created isAccelerating boolean to determine if we are speeding up or slowing down. If we're speeding up, this will be true. If we're slowing down, this will be false. And if we are maintaining our speed, this will be true, but that won't matter as our physical acceleration will be 0 and the character will not be leaning. I'll go ahead and get our physical acceleration 2D variable. I will get a vector clamp max size node. I'll plug in the maximum acceleration character movement component value, and they'll divide the resulting vector by that same value. This has now been normalized to a range of 0 and 1 in terms of length or absolute value. Now I'll unrotate that resulting vector by the previously calculated actor rotation variable, which we've named a world rotation. Finally, I'll use this to set a new variable named relative acceleration amount. I'll plug the true execution pin of our branch node into this set variable, and now I'll double click on this line to create a reroute node and drag it back to organize this a little bit, make it easier to follow and read. I'll copy this full grouping of nodes, paste it, and plug in the reroute into the false branch, the false execution pin of our branch, and I'll change this get max acceleration to get max braking deceleration. And now to recombine our logic flow, I'll give another reroute node and plug both of these set variables nodes into it. We don't have anything else to place after this, but we might in the future, and I did want to demonstrate that we can reconnect branching logic flows back together into a node or a reroute. Now go ahead and compile and save. Back in our animation graph, I'll drag out our relative acceleration amount. I'll right-click and split its struct pin. We're going to plug the Y value into the left/right and the X value into the forward/backwards. I'll compile and save, and now if I play, we'll see that the character leans forward into the direction of acceleration when moving forward and backwards when stopping, which I think makes the character feel a lot more dynamic and reactive to user input. This lean when we're walking, though, is a bit excessive. So what we can do is go back into our get acceleration data function, give ourselves a bit more room here, get our current gate, and get a select node. I'll plug the current gate into the index. I'll go ahead and between this on rotate vector and the relative acceleration amount set node, I'll get a multiply node. And I'll do this for both instances where we set our relative acceleration amount. I'll right-click into the pin of both of these, and I'll change this to a float. Now, if I plug the return value into one of these pins, it changes the values of the select node to floats. I'll plug this into both pins, and now what we're essentially doing is selecting a variable to multiply our relative acceleration amount by based on our current gate. And we're doing it with floats, as that's just a bit simpler and we only have to type a value one time instead of 3. So for walking, I'll set this value to be, let's say 0.25. And for jogging, I'll set it to 1. So now, we still lean into our acceleration when walking, but it is less noticeable. I think we could actually increase it a little bit, maybe 0.35 instead. I think that looks good. And believe it or not, that is going to be it for this iteration of our cycle state. We have actually finally managed to finish it. Now, eventually I'll show you how we can set up a cycle state in an alternative method, in an alternative manner using Blendspaces. But for the time being, we're ready to move on to other states fully, such as distance matched starts, stops, pivots, and an idle state that handles turn in place. As right now, you've probably noticed when we idle, the character turns when we turn our camera, and that is of course not our desired end result. And additionally, we'll eventually get to jumping too, and distance match our jumps so that they look even better. All right, everyone, that is going to be it for this video. And in the next one, we'll begin setting up some distance matching functionality for our Locomotion system. If you have any questions, be sure to leave them in the comments or in the Discord server linked below, and I will do my best to answer them. Thanks for watching, and I'll see you in the next video.